In this video, we're going to quick talk about graphing the derivative. And we've talked about this before, but it's worth just a quick review. First of all, I always look for the spots where the derivative is 0. And that's, of course, where the slope would be 0. Now, we've talked about tangent lines already quite a bit. A tangent line, remember, is a place that a line touches the graph once and at that spot has the same slope, something like that. Now, I bring that up because essentially what we're looking for here are horizontal tangents, spots where the tangent line would actually be horizontal and have a slope of 0. And we're going to be doing that, using that quite a bit in the upcoming days. So we're looking for where the slope is 0. It's right here and right here. I'm going to mark that in on my graph. Okay, so where the slope is 0, the derivative will be 0. Slope and derivative are basically interchangeable words in calculus. Next, I always like to look between the zeros that I found. Graph is decreasing, so the slope is negative, so the derivative is negative. Okay? So I'm going to just connect these, kind of a negative loop. And you say, well, how negative should it be? Well, that really has to do with how steep this is. We're just kind of eyeballing it right now. We're just going to say, well, it looks like it would go about this far. So it's not exact yet. Okay, over here, the slope is positive, so my derivative will be positive, like that. And it's going to just keep going up, the derivative, and getting more positive because it looks like here the slope is really steep, and it's, as if we extended this down, it would just be getting more and more steep, so it'd be really positive. So the derivative is getting really positive. Over here, the slope is positive, so the derivative will be positive. Smooth that out a little bit, something like that. Now we've begun to explore some of the rules and maybe seen some of the shortcuts, or at least we suspect some of the shortcuts. You look at this function, it's certainly, the original function looks like a cubic, and look at its derivative, looks like a parabola. And that's kind of one of the rules we've started to explore, is how we lose a power every time. In this example, we got a bit of a challenge because we know what we know about exponential functions. It never levels out, no matter what it really looks like. So the slope is never 0. It's always positive. And in this case, it starts off barely positive. And then it gets more positive, the slope does, and then it gets more positive, and then it gets really positive as it gets more steep. So the derivative starts off barely positive, then gets more positive and more positive as you go. Now, this is pretty important because it tells us a lot about exponential functions, that their derivatives have essentially the same shape. And certainly, I've kind of eyeballed this. You could have said, well, maybe it's a little more like that, or maybe it's, a little more like that. But it's essentially going to have the same shape. And again, we're just kind of eyeballing this. This is actually, the original function was e to the x. And you learn all the time in pre-calc that e to the x is very important. And when you ask why, you're usually told, well, you just got to wait for calculus. Well, we're getting to it. We're getting to why e to the x is so important. We'll hit it in the next couple days.